Hello, Frederick. Can you hear me?
Hello, Val. Yes, I can hear you.
Oh, fantastic. Very good. Hello. Great that you have time for me today. I should stress that you are not in Europe. You're in Peru.
Yes, thanks for inviting me, Val. Yes, I'm here at 9 o'clock in Peru, and all is well. Thank you.
You're in Lima now, and yeah, I should introduce you briefly. Frederick has been a master student and a postdoc here. Did his PhD in Australia, and then you've been in Tromsø for a time, and you're now an assistant professor in Lima. So, and it's great to speak with you today. And it's late afternoon here and early morning in Lima. So, but I asked you to talk with me a little bit about the new paper that you just published, and or that we have just published, because I'm involved as well, I guess.
Exactly,
So,
yeah.
And yeah, and it's a very intriguing paper because it's about submarine potential future ore deposits, submarine sulfides. And it's, of course, a very academic study. It's not so much about whether we should mine them or not. It's more about how they form. But of course, it begs the question. So maybe we can talk a little bit about this. But before we go into that, can I bring the paper up and ask you to run us quickly through the paper?
Yeah, sounds great.
Fantastic. So the paper just came out very recently. And here is the paper. Can you see my screen, Frederick?
Yes, I can see your screen.
Fantastic. So I leave it up to you. It's about the TAG, the Trans-Atlantic Geotraverse Sulfide Mound, and maybe you need to explain what TAG is first of all. But anyway, here you go. Let me know if you want me to scroll.
Yes, thanks, Val. Yeah, so in this paper, we studied the TAG Sulfide Mound. It's a submarine sulfide deposit located along the Mid-Atlantic Ridge. And this study was a collaboration between me, Val in Uppsala, Sabina in Tromsø, Ellen at the Natural History Museum in Stockholm, and Xin-Juan at the University of Minnesota. So if we maybe scroll down a bit.
Yes, I'll bring you to the map right now.
Perfect. So TAG is located here along the Mid-Atlantic Ridge, and here we can see a bathymetric map of the sulfide mound, basically forming a circular structure, and up here we have the active vent complex, which are now discharging high temperature hydrothermal fluids. It's about 200 meters in diameter, yeah, and contains 3.9 million tons of sulfide approximately. So it's a very one of the biggest underwater sulfide deposits that we know of currently.
That's quite substantial, and it's actually south of the Azores. Maybe we should add that along the mid-ocean ridge. You said that, but it's also kind of in pretty warm water. So it's not in some extreme kind of conditions in the Arctic or anything like that. It's actually in reasonably warm water, but it's far away from land. So, I mean, this is quite hard to kind of get to, I guess.
It is, yeah. And also very importantly, this was the first ever deposit to be drilled by the International Ocean Drilling Program. So here on the map, we can see some of these drill core sites that were sampled back in the 1990s. And
it's quite an amazing thought, isn't it? Drilling into this. I mean, how deep is this below the water level?
It's located, we can see here on the map, about 3.7 kilometers down. So yeah, so drilling these things it's quite a...
It's a technical challenge, isn't it?
Technical challenge, definitely.
This is over 3.5 kilometers below the water level. So, wow. So, and I'll bring us to the next figure, if that's okay. So, and here we have the drill cores, that's the blue bars. And I think your samples are the yellow little diamonds here, and here's some of the rock samples. And yeah, go ahead, Frederick. Sorry, I'm taking you.
No, that's quite all right. Quite all right, Val. Yeah, so here we can actually see a cross section of the deposit. So it comprises the upper sulfide mound, and then this is underlain by a stockwork zone of altered and mineralized rock in the basaltic basement that underlies the sulfide mound. And here, exactly, yeah. And here we have the drill cores, and we were lucky enough to get some samples from these drill cores, and we were able to sample some of the different textural types of sulfide. So here we can see, for example, massive sulfides, we have vein-related sulfides, different breccias, and here we can see the some pieces of altered basalt from the basement rocks underlying this. Exactly.
Yeah. So this is what's down there on the ocean floor in this particular part of the world. It's quite fascinating to me that we can actually get ideas about what's down there from drilling, and now we can study this. So, but the main work, as I said at the beginning, was actually very academic. It was looking at the isotope distribution, and in particular the iron isotope distribution.
Exactly. So we used a small micro drill to drill into some of these sulfide grains, and we extracted a few milligrams of different sulfides, including pyrite and chalcopyrite, and then we measured the iron isotope compositions of these minerals at the Natural History Museum in Stockholm. And here we can see some of the results, and kind of the main takeaway here is that the different textural types of sulfides show distinct iron isotope compositions. So for example, the massive sulfides have the lowest delta iron 56 values, whereas, for example, the disseminated sulfide in the altered basalt have the heaviest delta iron 56 values.
Yes, here we see the difference is quite dramatic, actually. And I should also point out the number of samples here. This is 50 samples overall, and it's distributed according to this kind of these numbers here. 50 samples is a lot. And I should also point out it's not cheap. I mean, each of these analyses costs hundreds of euros or dollars. So this was a big investment, actually. So I should stress this. So
it was, yeah.
It was. I mean, I realized. I remember when we talked about the project first, we had to pool resources in order to make sure that we can cover it all. So I guess it's important that people see that these things are actually quite expensive. So if you commercially buy one of these analyses, you would pay, I think, something on the order of $360 or $370 plus tax. So we're talking $400 for one of these samples or one analysis. So you can get a sense for this. So yes, but importantly, you saw a difference between the textural types, and I think this is what the real crux of the paper is. Let me scroll down a little bit, and here you have the kind of depth profile, and you see these differences here, and I'll zoom in a little more. So can you quickly run us through that?
Yeah, so as I mentioned before, we analyzed two minerals in the study, so chalcopyrite and pyrite. So if we start with the chalcopyrite, this mineral is very useful because it during its formation, it very quickly obtains isotopic equilibrium with the fluid. So we can use the chalcopyrite to kind of trace the fluid evolution through the deposit. And this was useful because we have a bit of data from other parts of the TAG hydrothermal system. So people have measured the vent fluid compositions and also the compositions of the hydrothermal plume. So following venting, the hydrothermal plume will then disperse over kilometers in the ocean. So now we could kind of complement these data with data on the sub-seafloor fluids prior to venting. And we found that there's quite little evolution in the fluid delta iron 56 values within the mound. So most of the iron isotopic changes happens after venting and also deeper down in the hydrothermal system, so during alteration of the basalt, and not very big changes in the fluid compositions within the mound. And this is important when people try to trace the origin of iron in the oceans, which is of course very important for biological
It's an
productivity.
important nutrient, exactly.
Yeah,
And
exactly.
it comes from these kind of vents, you know. I mean, these are
Mm,
often also places where primitive communities settle, and it might sound
mm,
very hostile to us, but a lot of
mm.
deep sea communities actually kind of cluster around these vents. It's very important, and it's not just about ore deposits here. Sorry, I just
Exactly.
interjected here, but
No, that's
you're
quite all right.
absolutely right in stressing that.
Mm. Yeah, and
So,
with the iron isotopes, we can then distinguish the hydrothermal iron from other iron
yes.
sources. You know, and so this is why it's important. And then we also analyzed pyrite. And pyrite works a bit differently from chalcopyrite because it's characterized by a lot of isotopic disequilibrium. And here we relate these different changes in the pyrite iron isotopic values to different degrees of both of the precipitation mechanism. So the pyrite that forms in more superficial levels of the mound, they usually precipitate due to hydrothermal fluid seawater mixing, so a very rapid formation. So this pyrite is characterized by a lot of disequilibrium, and this is reflected in these light isotopic values.
Yes.
Whereas the deeper pyrites form more
So
from
you were talking
conductive
about these
cooling.
guys here, yeah.
Exactly, yeah. And the deeper pyrite types, they form more from processes related to conductive cooling. So here we have a bit more slow pyrite formation. And this allows the pyrite to obtain heavier values because it has more time to equilibrate with the fluid. And then superimposed, exactly. And then superimposed on this, we have a process of hydrothermal maturation where pre-existing sulfides are interacting with later fluids, and this causes additional re-equilibration isotopically in the pyrite. So it drives the iron isotopic compositions of pyrite towards heavier values, which we can see here in this arrow in the middle of the figure.
Yes.
So we think basically that these textural differences in the pyrites are related to the precipitation mechanism and this process of hydrothermal maturation throughout the mound.
Yes, that was the big conclusion. Very good, thank you. And there's a few data from some of the other drill cores, but the data density is not as high. And do you want to say something about them, or are you happy to leave it at the main section?
No, for example, we can see here, for example, at the very left in the TAG4 area, here we find the lightest isotopic values in the whole mound. So here we think that the hydrothermal maturation has been less extensive compared to the other parts of the mound. And this is also evidenced by, for example, the mineralogy and the ore textures in this part of the mound, which are significantly less mature than other parts of the mound. So the iron isotopes tells us a lot about the hydrothermal maturity of the sulfides in general. So
and how they likely form at depth and how the different parts come together. So this will of course be useful in the long run for exploration. And this is the end of the article. It's a very short article. It's published in a new journal called Communications in Earth and Environment. It's part of the Nature Portfolio Group. So, and you can download it. It's open access for everybody who is interested. And there's also some supplementary material and additional information here that you can access. But this brings me on to a somewhat bigger discussion beyond the entirely academic aspect that is mainly our interest. It brings me on to this discussion, and this is a bit like, you know, there's a lot of metal down there, there's a lot of iron down there, there's a lot of copper down there, and it's bound with sulfur, so it's sulfides. We can process that. I should point out that in Europe, we still get a lot of iron from places like Russia. And I think we want to be as independent as possible from players that we cannot control, from international players, that is. And then, of course, going submarine, given also the needs for, you know, more materials in the future, more metals in the future for green technology, it creates a need for doing something about it. And one potential option is frontier minerals, as it's known, and that is, you know, deep sea. and space mining and things like that. But here on the Greenpeace webpage, as they quite pointedly kind of note that, what are the minerals used for that we get from the submarine deposits for clean technology? So there's this bizarre twist that if we were to mine them, we would actually ruin environments in order to save the environment. And I don't have the answers to this about whether it's right or wrong, and we're still miles away from mining it. But what do you think about this? What's the chance of TAG being actually a real ore deposit, not just a reserve or something that we have in mind? Do you think people will actually be able to go there and extract it one day?
Yeah, definitely. I don't have all the answers either,
Sure
but I think
don't.
it's definitely an interesting prospect. We're rapidly depleting, the metal resources here on land, and as you mentioned, there's these geopolitical aspects as well to consider. For example, in Europe, it's very important that we become more self-sufficient with regards to metals. And obviously, yeah, these underwater deep sea deposits represent a significant source of many metals that we need in order to be able to carry out this green shift, as we call it. I think definitely there's a lot of work that has to be done, assessing the potential for these deposits, both from a technological aspect, how do we get the metals out? Also, there's many environmental aspects to consider. Can we do this without actually destroying the environment too much? I know, for example, I worked in Norway for 2 years during my postdoc, and here it's there's heavy interest from both industry and the government to try to really assess the viability of their deep sea mineral resources. They also have a lot of offshore experience from the oil industry,
Yes,
for
they do.
example.
Absolutely.
Yeah, so there's, for example, in Norway, there's a very serious effort going into potentially assessing the viability of all of it.
Yes, because it's a difficult issue, and I was just recently publishing a short opinion piece where I commented on the problem that when people argue they don't want mining here in Europe, they don't want mining in their backyard, which I kind of understand, but the problem is that the need for metals is so enormous that what you're doing is by not mining in Europe, you're partly pushing the problem elsewhere. You're pushing it into regions of the globe where mining is less regulated, where environmental regulations are much poorer, where work and labor conditions are much poorer, where the actual miner will not get as much paid as it is, for example, in Europe, and conditions are potentially quite terrible. There's also artisanal mining where there's no regulations whatsoever, where child labor may be quite a reality for some metals. And here's the thing, I mean, I think if we go submarine, if we do this in a organized way with a very careful impact assessment, and we only do it very localized, only at very selected spots, i.e. not grazing off large areas on the seafloor, but doing it in, this area is a few hundred meters by a few hundred meters. If we were to do that, maybe this is not completely out of the question, and maybe we can control the damage. But the damage we see in certain parts of Africa or China is just, whoa, it's so uncontrolled that I actually think it's worse than what we could do in terms of damage submarine. But I'm not a specialist for deep sea biosphere and things like that, so maybe I need to stand corrected if somebody knows better. But anyway, that's my kind of consideration right now. So interesting problem, isn't it?
Definitely, yeah, you made some very good points there as well. So yeah, we'll have to wait and see. I think we're still definitely at least 10, 15, 20 years away from this actually becoming reality, potentially in the future. So we'll have to see how it all plays out, but definitely there's a lot of assessments to be made.
Absolutely.
But importantly, in the meantime, these deposits are of course very important because we can find ancient analogs of them actually on land. So by studying these active deposits, it tells us a lot about how these deposits on land actually formed and how we can look for them and so on. So they play a very important role also for on-land mining.
Absolutely, you're absolutely right. We discussed this at the end of the article, and maybe we almost forgot about it. But of course, this knowledge about what forms will help us about working out where things are in onshore deposits, because for those people unfamiliar, when plate tectonic strikes, sometimes we get slivers of ocean crust being pushed on continents, and we then find some of these submarine ore deposits on land in some mountains even. And then we need to kind of think about how did they form, where would we need to dig, because in the mountains we need to dig shafts and things like that. And then understanding how they're formed will be crucial. It will save us a lot of money, pain, and labor to actually understand how they look like. So beyond the question of whether submarine mining is the thing of the future or not, there is a direct application for onshore mining and improving the quality of mining and trying to reduce damage for the environment by being far more targeted and less random about exploiting these deposits onshore. Thanks for bringing this up, Frederick. You're right. That's a very important point. So, okay, I think this should give everybody a good idea, and I will put a link to the paper in the box down there. So if people are interested, you can download the paper. And well, Frederick, I say thank you for your time. Thanks for running it through that. Very much appreciated. And congratulations on your paper. It's a great success also scientifically. Thanks a million.
Thank you very much, Val. Thank you very much for inviting me. It was great to chat with you.
Okay, then I say goodbye. All the best to Lima and good luck.
Thank you, Val. Goodbye.